Welcome everyone. Thank you for attending this session. I am Rafael Souza and I work for the Software Applications Group at Texas Instruments. Today we will cover the topic of how to set up Code Composer Studio version 5 to perform Linux debugging. I hope you enjoy it. The agenda today covers some basic concepts necessary for the overall Linux debugging process, followed by specific methods for each case. Application debug, which uses the built-in Eclipse features of Code Composer Studio, and low-level debug, which uses the JTAG emulation traditionally used by embedded developers. At the end, a demonstration of each method will be shown directly on the tool. Originally, Linux was not developed for embedded systems, but due to its popularity, it was quickly adopted for TI's system-on-a-chip embedded processors. Since the constraints of the embedded world are much more restrictive, but Linux is still a high-level operating system, the debugging process requires different skills and brings together two types of developers with very different backgrounds. An embedded developer used to use hardware-oriented debugging tools with complete control of the running processor has to deal with the fact that most of the development and debugging in Linux is done in an environment that interacts with other software components that run simultaneously and do not have exclusive control of the system. This environment is called the user mode. A Linux developer, on the other hand, may have to go a level closer to the hardware where the debugging environment requires a deeper understanding of the underlying hardware and the software interactions can cause a system disruption. This environment is called the kernel mode. Just to visualize the differences, the picture shows the several layers from the hardware in the bottom up to the higher level of the operating system. The user mode is what we see in a terminal or in a graphical environment when Linux is up and running. That's where user applications, frameworks, and libraries are located, the upper part of the picture. The kernel mode is everything else that is running in background and is responsible for the control of all low-level software and hardware support. Low-level software comprises memory and process management, protocol stacks, file systems, while hardware support are device drivers and core processor code, all located in the middle part of the picture. Now let's dive in the process of debugging Linux applications. As you can imagine, the Linux applications are the core element for system-on-a-chip embedded systems as they carry most of the value-added software for a product. Therefore, the developer will typically spend most of his time in debugging applications that run in user mode. And to help with that, a popular open-source utility called GDB is used. The utility itself is comprised by two components. The GDB server is the component that is responsible to load and control the application under debug. In our typical embedded environment scenario, GDB server is executed in the target processor to control the target application. It requires a stable Linux system running in the development board or custom hardware, as it is invoked by commands issued via terminal program. The other side of the debugging system, the GDB, sends commands to GDB server through a text-based user interface. In our typical embedded environment scenario, GDB runs in the host PC and itself is controlled by the Eclipse IDE. This picture illustrates the Linux application development environment from a software perspective. You may have already noticed, but I'll emphasize it anyways. Linux application debugging can be done entirely with open source software. The host PC on the left can run any operating system. In our environment, it can be either Linux or Windows. Also, you must have GDB and an optional debugger IDE. In our environment, the GDB is provided by a third party named Code Sorcery, and the debugger ID is CodeComposer Studio. You can see from the picture the IDE encompasses GDB, as it completely controls it. At last, the host PC must have some terminal program to interact with the Linux running on the target board. In our environment, PuTTY will be used, but Hyperterminal, Teraterm, Minicom, or others could also be used. The target board on the right must have a running Linux environment with both the GDB server and the application binaries on its file system. In our environment, GDB server is running on top of the Linux distribution provided by DVSDK. It is invoked through the terminal program, and you can see from the picture it encompasses the application, and it must have complete control over it. This picture shows an example of the physical connections between the two systems. The RS-232 is a typical serial port that is common in TI's development boards and is used to interact with embedded Linux. The LAN is a typical Ethernet network, also common in TI's development boards, and is used to carry the GDB interactions. The connections can vary depending on the configuration of both systems. For example, GDB can run on the RS-232, or the terminal can run on the LAN. Although the debugger IDE is optional, Eclipse is a great solution to do efficient application debugging. GDB is part of the open source GNU toolchain, a very popular tool used to develop Linux applications, and Eclipse supports it natively. It is also highly extensible with several plugins provided by the community. Although most of debugging is done user mode, in the course of the product development, it may be necessary to perform debug at lower levels of a Linux system, but these are not easily accomplished by using software-only solutions. One way to accomplish this is using KDB, a modified version of the GDB that has access to the kernel mode and allows debugging certain parts of the core components of Linux. I am not very experienced in KDB, but I have heard that it has limited visibility on the system. Also, differently than debugging in user mode, the kernel mode debugging may or may not have a stable Linux system running, as sometimes the focus of the debugging process is the initialization and/or stability of the system. KDB would not be helpful in this scenario. Therefore, another alternative is to use external hardware, in our case a JTAG emulator, which allows much better control of the environment and goes very deep into the processor's hardware. Given this capability, the debugging environment must be tailored to the processor itself, thus requiring additional support from the device or board manufacturer. This picture illustrates the low-level debugging environment from a software perspective. Notice the differences between this and the application debug. The only required components are the debugger IDE and the software running on the target. In our environment, the debugger IDE is CodeComposer Studio, and the target software is the Linux distribution provided with DVSDK. This picture shows an example of the physical connections between the two systems. As expected, the only connection required is the JTAG emulator. A specific 14 or 20 pin connector is available on TI's development boards. The RS-232 serial port is completely optional, but extremely useful to boot the system or observe and control the Linux environment. As mentioned before, this port is also commonly available in TI's development boards. The beauty of using an external JTAG emulator is that it opens more debugging possibilities. In several of TI's system-on-a-chip devices, there are other core processors that can be accessed directly at low level. This makes multiprocessor debugging entirely possible. Also, it allows debugging the system during boot and initialization. A very difficult, if not impossible task, if only software tools are available. Although application debug can be done entirely with open source tools, Code Composer Studio brings low-level debugging to the same Eclipse IDE interface. It does the task without breaking compatibility to the existing open source Eclipse. Also, there is the option of using the low-cost XES100 JTAG emulator, a $79 or $89 if I'm not mistaken. With this emulator, Code Composer Studio can be used free of charge. If faster and more advanced emulation capabilities are needed, a good option is to use an XES560 V2. These emulators also have Ethernet connections, which is great for remote debugging. With this emulator, Code Composer Studio 5 can be used for free during a limited time, 30 days extensible to 90 more. The debugger in Code Composer Studio can do simultaneous application and low-level debugging, which is very useful for applications that access device drivers or modules, for example. It also has the capability of synchronizing breakpoints and some events through multiple cores. If you're familiar with TI's System on a Chip or any multi-core devices, you know how difficult this task can be. The compatibility with Eclipse CDT is not broken, which allows the use of third-party plugins for several other operating systems. The debugger can be attached to existing OS source code and give the traditional low-level debugging capabilities shown. Also mentioned before, a Linux version is available and several hardware JTAG emulators are supported. The link has a list of all the features supported. At last, all the other productivity plugins can be used with Code Composer Studio 5. Demo time. This picture illustrates the setup environment of the demonstration. It is a VMware with Ubuntu 10.04, 32 bits, and it has installed both Code Composer Studio 5.1 and the OMAP 3530 DVSDK with complete Linux kernel sources. It also has a Blackhawk XDS560 V2 connected to the USB port of the host PC. I am running it in a small private network to connect the two GDB components, GDB and GDB server. So this is our environment for the demonstration. It's a Ubuntu 32 bits, 10.04, running on a VMware machine. And I have installed also Code Composer Studio 5.1 and the DVSDK for OMAP 3530. That's the board that we're using. So I'll first run my terminal program to start Linux, and just turning on the board here. There you go. So the board will boot Linux. Let me just confirm if it's going. There you go. So it's going. So while Linux boots, I'll actually open a Code Composer Studio, and in the meantime I'll actually select a new workspace. Oops, it failed a little. Okay, just a little hiccup on the Linux load. And then I'll select my new workspace. I'm starting fresh just for the purpose of this demo, and that's the screen that you actually would get whenever you start install Code Composer Studio in your machine. So you see it's all empty. So basically, once actually Linux finishes booting, there you go, we have Linux finished booting. I still didn't log in yet. I'll just explore now the capabilities of the low-level debugging, because, as I mentioned, it's not necessary actually to have a stable Linux running. In this case we have, but we could actually access the Linux entirely before the prompt itself. So in order to do this, we have to first tell CCS where to look for the source files. So in this case, because I have dvsdk installed in this system, I can actually simply create a new project that has makefile that references all the Linux sources. Because Linux is built with a makefile, then I simply create a new project with existing code, a makefile project with existing code, and I can point to my dvsdk installation exactly where the Linux sources are. There you go. Therefore, when I click finish, it imports, creates the new project with all the sources available. And at this point, which is very important, if you feel a little bit slow your system, keep in mind that here's the Eclipse indexer is running now. Why? It's actually doing its job of creating a big table with all the symbols and variables and source files, so to create a proper correlation with whatever you have in your source files and target, basically what is running already in your target. So that's pretty much the indexer doing its job. So after the project is created, I can actually browse into its all source code, and I now have to create a configuration that connects to my board. With the magic of editing, I'll wait until the indexer finishes running. And we are back. Now we see that the indexer has finished execution. It's a great thing to help with the performance of the debugging session. So what I have to do now, after I actually have my project, is actually have a way to connect to my target, meaning my target board, through the emulator. I need to configure CCS to do that. So in this sense, I can actually go and check whatever target configurations I have. Of course, this is a fresh installation, so I have nothing in here, either inside a project or as a user-defined configuration. I can create mine, and the only idea is that I have to remember what is my hardware configuration right now. So I have an OMAP 3530 EVM board connected to a Blackhawk 560 V2 through USB port. That's how I usually tend to name my configurations. Usually they carry something meaningful. So what do I do now? It's a typical Code Composer Studio procedure to create a target configuration. I can select my emulator from my drop-down menu. That's the type that I have, and I simply check the device that I'm using. Okay, important. I saved the configuration, but it's actually a very important detail. Several of these configurations, of these device configurations, are designed for, to do standalone debugging. Basically, when you have the scripts that actually perform initialization of the target and of the board. So what happens is that by selecting this configuration plane, it comes with these scripts pre-selected. Some of these devices do have that. So what happens is that if I have a system running on the target already or about to be initialized, we need to actually let the software running on the target do its job. If you see here in my Linux, it already initialized a lot of things, network and memory and etc. So these scripts actually will get on the way of my current running Linux setup. So what I wanted to do, click on the tab Advanced and simply go ahead and remove the initialization script from the configuration. That is very important. Okay, sometimes if you're going to debug on the DSP, you want to remove on that or any other cores as well. In this case, it would only be needed to remove for the Cortex A8. Now I save. My configuration is now created, so I can close it. That's fine. This is just, it shows up as you can see as a user defined, and it is in bold, meaning it's the default configuration that I could launch. Going back to my project browser, I now have to find a way to attach the configuration that I just created with these source files, these source file trees. Okay, so the idea now is that I have to actually create my debug configuration straight from the debug configurations menu. I simply right click it on the project, and basically what you want to see, although the screen is actually kind of small, I wanted to do a Code Composer Studio debugging session. Remember, this is a Code Composer Studio feature, not an Eclipse, a standard Eclipse feature. So that's where you want to go. So I can create my new configuration, and that configuration will actually reference my existing target configuration that I just created. And I don't necessarily need an initialization script, and here I can select which cores I want to debug. Usually the less the better, because it increases performance. That's always a good idea. I also can name my new configuration as something actually relevant. That will be a good thing. Okay, I created this configuration. Now I actually have to attach on the tab program. I actually have to attach the project that I have currently running to the core that is running. Okay, so basically the idea here is that I have multiple cores. I can attach multiple projects to each core, actually one project per core. So I can actually, in this case, I'm going to actually observe or debug the Linux that is running on the Cortex A8 core. So I have to select it from the drop-down menu, and I go into the workspace and select my Linux project. That Linux project will attach, this line here will attach all the source code to my debugging session. However, there's another detail here. In order for the debugger recognize what's going on the target, what I have to do as well is attach it to a file that has symbols, debug symbols, so the debugger can correlate whatever is in the target to whatever source code or source file the code is in. So what I have to do here, by default, Eclipse thinks that you're building this project from inside its own environment. That's why it creates this big environment, this big variable here, this big string here. However, that's not our case, because we don't build Linux from inside the Eclipse environment. So what we do is actually select a valid file that I have, that I happen to know that matches whatever I have on my target running right now. This file is actually a file that carries the debug symbols, and in this case it's actually inside my targetfs boot directory. That targetfs is mounted to the target board, and boot actually happens to carry the same copy that I'm running on the target right now. This is VM Linux is the file that actually carries the debug symbols for a Linux kernel. The uimage is the one that it's the executable, so has no information there. Okay, so I'll reference this file, and as I mentioned before as well, I wanted to actually simply load symbols. I don't want to load the program. Similarly to the GL scripts that I mentioned before, if I load the program, I'm going to disrupt the existing Linux session. I don't want to do that, not at all. Okay, so we are pretty much done, apart from one detail, so I can actually simply apply my changes here. So I actually have created my debug configuration, but I just want to make sure of one thing that I actually forgot when I created my project. By default, Code Composer or Eclipse builds the project before launching the debug session. I don't want to do that. So what I have to do before I actually launch the debug is actually I want to disable the build process on my Linux project. Again, I don't want to build the project from inside CCS. We actually do need to build Linux kernel from a command line. It has its own sets of scripts and etc. So I don't want to do that. Okay, I'm pretty much done and set. So what I have to do now is simply launch the configuration and connect to the target. I can simply go either here on this small triangle here, and then I go to my debug configurations from here, or I can right click on the project as well and go to my debug configurations and select the configuration and simply launch debug. Once it is launched, you will actually have an entry on the drop down menu of the button that I pressed before. It will allow to quickly launch the configuration from there. Okay, so I hit debug and I wait for the debugger to launch. Again, this is the first time that it's being launched, so usually it takes a little bit longer, so it's actually creating the entire cache information. So you can see a little bit of progress in here. So with the magic of editing again, I'm going to skip to the end of the debug launch. So it finished launching. So you see that we have the correlation here, perfect correlation between the call stack, where I see everything that was called before the function map3pm idle, and with this I can also see the disassembly, which also has the code correlated, including the line numbers in here of the source or the source file attached to this memory address. And I can also, in this case I don't have local variables, the variables view does not show because I don't have any local variables in here, but I could also put any expressions in here, expressions meaning it's like a watch win, a traditional watch win. I could actually observe variables and say things like that. And I can also take a look at the registers on the device. So that is the kind of functionality, deep low-level functionality. We are actually looking into the hardware very seriously here. You can also set breakpoints to stop at specific places in your code. You can simply double click on the side of it and the breakpoint viewer will show that accurately, and then you can set multiple of them. You can also enable or disable them. This is actually useful for if you actually are trying to monitor within a range or while running a single application. In this case as well, you can notice that I connected. You can tell that the program counter is actually halted at this specific instruction. So what we have in the Linux side is that we don't have anything working. I just typed root and nothing showed up in the terminal screen. Why? Because Linux is absolutely halted at this point. So what I do here is, if I actually want to regain the Linux environment, I can simply go to resume, and there you have it. What I typed before, there you have it. There's root right here. And then I have again a working Linux session. Now we can start the Linux application debugging. For this, you have to have a stable Linux running on your target, and you have to have also an application. To create an application, I can either have a project in Code Composer Studio, or I can simply use an existing application, a binary from an existing application. In this case, I'm going to create my my application from Code Composer Studio. In the project development perspective, I can either import an existing project that builds my Linux application, or I can create one from scratch. Because I'm using the Eclipse native capabilities to build a GCC project, I am selecting a C project under C++ instead of under CCS. Here I can give a significant name for my project, which calculates some sine waves for the Cortex-A8 core of my OMAP 3530 processor. I'm going to create an empty project for Linux using GCC. The project is created, so let me just close this Linux project here, just reduce it so I can better visualize everything. Now, with the project created, I need to actually configure it for my cross-compile tools, meaning the tools that I'm going to use to build to my target board, not to the native Linux, to the Linux running on the PC. And I also need to add some source code to it. So I'm going to do it first. I can add a project file by using the menu project. Oh, okay, here's an important thing. Eclipse, because you're actually creating a project for standard Eclipse C++ development environment, Eclipse naturally changed the perspective to its standard C++ development perspective. Instead, we usually use the CCS edit perspective. So you can notice the difference between the two by starting with the menu and the organization of the windows. We added a feature that actually helps adding files to a project from here. In this case, I already have my source file that I can add, and now I have my source file in here added to my project. Now I can configure the project options that properly add or configure my compiler tools for the cross compiler that I have installed in the system. The compiler tool that I'm going to use as a compiler and linker to build my Linux application, they are actually installed here in my system in a specific directory, which I happen to know. They are here. Those are my tools that are installed in this directory. Therefore, I need to actually pass the entire path with the name of the tool itself. So that's the entire path. And now I need to give the name of the compiler itself, which is this one. I configured my compiler command. That's the tool that is going to be used to compile my code. The same tool is used for the linker. So I can simply copy and paste the tool on my linker options as well. The next step to properly configure my development environment is to appropriately include the correct directory that holds all the standard C include files like standard IO and others. So in this case, in this option, I can actually specify the specific oops, I selected the wrong one. I can specify the path to add the include files. In this case, for the code sourcery tool, they are usually installed here. So that's the path for my include directories. Also, the same thing happens for the libraries. I need to include a directory where the linker can find the library to properly link my Linux application. In this case, the same thing. That is the path, complete path. With that, I'm almost concluding the entire settings of my project. What I have to do now is actually set all the architecture dependent options. And this is actually very specific to the cross compiler that you're using. Therefore, Eclipse does not have graphical configurations for that, but instead it shows a text box where you can type all your options in here. Fortunately, I have a small trick where I actually already saved all the options that I need that are very tied to the architecture that I'm using. This concludes all the project settings necessary for the cross compiler on my project. Now the only step needed is to simply build my project. Build successfully. My binaries are in here. They're under the debug directory, and now I can proceed to create a debug configuration and debug this project on Linux. But before I do that, keep in mind one thing. My binary, my application, the sine wave A8, must be located in the board because I need to run it from the running Linux. And then I'm going to run it on the GDB server session on the target board, and I'm going to run Eclipse with GDB on my host PC. Therefore, I have to find a way to copy it to my target board. Using the way I'm configured this system is that my target board is properly using the file system of my host Linux PC, actually loading it via NFS, via a shared networked file system, as we call. So this file system is actually located in this directory. That is my file system that is actually loaded into my target. And then I simply need to copy a file to this directory or to a subdirectory of this directory, so I'll have access to it from my target board. So This directory, for instance, here in my board is home root, and here that's the exact same directory. Oops, some extra F's in here. There you go. These are two pointing to the exact same directory. Whatever I copy here in my Linux, it will be reflected here. So I simply need to copy this file into this directory, the sine wave A8 binaries into this directory. I simply copied the executable and it magically shows up here. That's the beauty of the NFS. So I have my application running on my target, and I simply can run a session of the GDB server. I need to specify a random, actually an arbitrary port and the name of the application. So I have GDB server already running on my target. Now I need to properly configure Code Composer Studio to communicate with my target. So I can go back to my Code Composer Studio session. Similarly to the Linux kernel debugging, I can add my own debug configuration. In this case, instead of running a Code Composer Studio device debugging, I'm actually going to do a C++ remote application debugging, because my application itself is on a remote location. It's on a target file system. So I create a new configuration, and because I had the project already selected on my perspective, he already picked up automatically all the information from the project, which is extremely convenient. Okay, so I have the application, I have the project itself. Now I need to actually specify how am I going to connect with the target board. For that, there is an option, a hidden option, almost hidden option here, where it actually tells me how do I want to actually connect to my remote application. In this case, by default, Eclipse has an automatic launcher, but for our case, since we already have a Linux session running on my target, I want to do a manual remote debugging launchers. And Linux is already running my application on the other side, so that makes perfect sense. So I now selected my remote debugging. Now I have to configure the debugger itself. In this case, in this screen, similarly to what happened with the compiler tools, that I actually had to select the code sorcery cross compiler. Same thing here I need to do for the GDB debugger. Why? Because the GDB debugger by default here, it understands the code for the host PC, meaning the Linux code that is running on my PC right now. However, I have to have a GDB that understands whatever is running on my target system, on the ARM processor that I'm running on the board. Therefore, I need to point to the GDB debugger that actually I have installed in my code sorcerer distribution. So I go here again, and I go back to my target file system, code sorcery, and then I'll do this again. Here's my GDB right here. So I can simply copy and paste all my paths. Now I have my debugger pointing to the correct GDB. And finally, I need to specify the type of connection. How am I going to actually talk to my GDB server on the target board? In this case, I'm going to communicate through the network, so TCP, and I have to actually give the number of the port, which is 10,000, and the address of the board. And that's something that I can find. I usually forget to get it, so I always need to scroll up and get here. That's my address. That's the address of the board. And the port, where did I specify the port? The port I specified when I invoked GDB server. That's the parameter. So I am good to go now. Simply do apply, saves all the changes, and now I'm going to hit debug and connect. Now the GDB session is launched, and you can see that the program, my Linux application, is stopped at main, and I have the disassembly window here, and I can see also the local variables in here, and its values, and I can also evaluate expressions, see registers, and etc. And in this case, I can also step into functions, step over functions. For example, you'll notice here that you simply change the value of the variable, and I can do many things with the debugging. I can also have breakpoints, and one important detail is this. This is a Eclipse. Actually, it's a GDB session, debugging session, and it has all the breakpoints implemented in software. Also, you can confuse with the Code Composer Studio debugging session, which also has breakpoints, but they are usually harder breakpoints. So one thing to be extremely careful when you actually are going to set a breakpoint in a debug session is to make sure that the breakpoint is set to the correct debug session you're running. For instance, in this case is GDB, so I can actually right click on the line that I want to add the breakpoint and set the breakpoint types. In this case, the type of breakpoint is correct. That is the standard Eclipse breakpoints, or meaning the GDB breakpoints. You could also select the harder breakpoints, but they are useless in a GDB session. So I can, with the proper type of breakpoint selected, I can double click on the line, on the desired line, see its location in there, and run, and that's it. So you actually can have it. This is one of the important points when doing debugging in such a mixed environment like this. In summary, Code Composer Studio 5 is your one-stop shop for Linux debugging. Although the application debugging can be done with open source components, the addition of a JTAG emulator greatly increases visibility to the debugging process and is critical for product development. The procedure you just saw is also shown in the link at the bottom. Thank you for attending today. I hope you enjoyed the presentation and have a great day.